Lesson 3-3, complex numbers. In your math studies so far, you have worked with real numbers. However, some equations such as x squared plus x plus 1 equaling 0 do not have real solutions. This led mathematicians to define imaginary numbers. The imaginary number, or the imaginary unit, I, is the principal square root of -1. Thus, I is equivalent to the square root of -1. And I squared is equal to a -1. Why would that equal to a -1? Because if I have the square root of -1 times the square root of -1, when I multiply a radical by itself, it becomes the radicand. So that would be a -1. When we're looking at complex numbers consist of a real part and an imaginary part. And the imaginary part has this imaginary unit, I, involved. So numbers of the form 6i, -2i, and I squared root of 3 are called pure imaginary numbers. A pure imaginary number is a number in the form of bi, where b is a real number and I equals the square root of a -1. For any positive real number, square root of -b squared equals square root of b squared times square root of -1, or just think of it as bi. Commutative and associative properties of multiplication hold true for pure imaginary numbers. The first few powers of I are shown below. So the first power is I squared is -1. I cubed is I squared times I, or -1. Because I squared would be -1. -1 times I just gives you a negative I. So here we want to simplify radicals and find the square roots of negative numbers. So we're going to be dealing with imaginary numbers here. For this one, I want to break this apart. So I have to take care of this negative. I know that that's going to be a square of -1. And then this is going to be times the square root of 294. Now I want to break down the square root of 294. So if I break this down, this could be, so if I did 294 divided by, we divide that in half. So this would be like the square root of 2. This would be the square root of 147. Now I got to think, what can I multiply 147 by? Or what can I multiply to get 147? So if I divide that by, let's say divide that by 7, I now have the square root of 7 times the square root of 21. This could be the square root of 7 and the square root of 3. Now I have a square root of 7 times the square root of 7, which is 49. So this is the long way. So this is the square root of 7 times the square root of 7 is the square root of 49. Square root of 49 is 7. So this will equal 7. And then I have a square root of 2 times the square root of 3, which is the square root of 6. The square root of -1 can also be represented as I. So my final answer would be 7i square root of 6. Now that is a longer way of writing that. We could have just done square root of 49 times the square root of 6. And then this would give us 7 times the square root of 6. And then we also have the square root of -1, which would have been I. Next, simplifying the square root of -75. So if I rewrite this, this is the square root of -1 times the square root of 75. I can do perfect square. Square root of 25 times the square root of 3. Square root of 25 is 5. Square root of 3, and then the square root of -1 is I. So the choice that would make sense here would be letter C. Next, simplify the square root of -80. So I have negative square root of 1 times the square root of 80. Break this down with a perfect square. So this would be, I did square root of 4 times the square root of 20. Let's do 16. Square root of 16 times the square root of 5. Square root of 16 is 4. Square root of 5. And this is I. So my final answer would be 4i square root of 5. Next, Here we are multiplying products of pure imaginary numbers. So the first thing we're going to do is get the imaginary number out. So this is square root of -1 times the square root of 10 times the square root of -1 times the square root of 15. The square root of -1 gives you I. And then I can break down the square root of 10 and the square root of 10 times the square root of 15 would give us the square root of 150. Then I can break this down. So square root of, we did 150 divided by, let's do 25. So square root of 25 times the square root of 6. Square root of 25 is 5. Square root of 6. And then the square root of I times the square root of I gives you I squared. And we know that I squared is equal to -1. So -1 times 5 square root of 6 will give us -5 square root of 6. Next example, simplify this one. So if I take this, I know that this is I and the square root of 16 is 4. So I know that's 4I times an I, and the square root of 25 is 5. And I would have 4 times 5 is 20, I squared, which would make this equal to -20. Next, I have negative, this would be square root of -1, square root of 7 times square root of -1 times the square root of 49. Square root of 1 times the square root of -1 times the square root of -1 is -1. This is a 7 times 7 times the square root of 7. So my final answer would be -7 square root of 7. A couple more. Here are equations with pure imaginary solutions. So here we're going to solve for x. So to do this, I'm going to subtract 81 on both sides. And now I have x squared equaling a -81. 1 to a square, we find the square root of both sides. And now I'm left with x equaling square root of -1 times the square root of 81. Square root of -1 is I. Square root of 81 is 9. So x would equal 9i. Now, because we're finding square root of a number, we do have two roots. So this would be a positive and a negative 9i. Okay, so this is a positive and negative I. Next one, solve this one. So we're going to subtract 27 on both sides. We now have 3x squared equaling a -27. Divide by 3. I now have x squared equaling a -9. Find the square roots of both sides, and I'm left with x equaling square root of -1 times the square root of 9. So this will give us I times a positive and -3 equals x. So x would equal positive and -3i. Next, solve this one. So subtract 64. I have 4x squared equals -64. Divide by 4. X squared equal -16. Find the square root of both sides, and I'm left with x equaling. I'm just going to go right to the I, plus or minus 4. X would equal plus or minus 4i. So just know that if you have a negative involved in there, there's going to be an I on the outside. Next part is complex numbers. So complex number is any number that can be written in the form of a plus bi, where a and b are real numbers and I is the imaginary unit. A is called the real part, and I is called the imaginary part. So we always want to have the real part first and then the imaginary part. The Venn diagram shows the set of complex numbers. Notice that all the real numbers are part of the set of complex numbers. So if this whole thing is complex numbers, you have real numbers and you have imaginary numbers involved with here. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. Commutative and associative properties of multiplication, addition, and the distributive property holds true for complex numbers. So to add or subtract complex numbers, combine like terms. That is, you're going to combine the real parts with the real parts and combine the imaginary parts with the imaginary parts. Two complex numbers of the form a plus bi and a minus bi are called complex conjugates. The product of the complex conjugates is always a real number. And the reason why it's going to be a real number because I times I, remember, is I squared, which would make it -1, and b is a real part, so we're just going to have a negative form there. A radical expression is in the simplest form with if no radicals contain fractions and no radicals appear to be in the denominator of a fraction. Similarly, a complex number is in its simplest form if no imaginary numbers appear in the denominator of a fraction. You can use complex conjugates to simplify a fraction with complex numbers in the denominator. This process is called rationalizing the denominator. So we're going to find the values of x and y that make 5x minus 7 plus y plus 4i equal to 13 plus 11i true. So to do this, we're going to just work with our real parts. So real part is 5x minus 7 and 13. So I'm going to have one equation as 5x minus 7 equals 13. So this is the real part. And then the imaginary is anything with an I. That would be y plus 4i equaling 11i. Then we're going to solve for x and we're going to solve for y. So here I'm going to add 7. And I now have 5x equaling 20. Divide by 5. X would equal 4. And on the other side, we are going to combine our y's, so the imaginary parts. So if these are all imaginary, I'm going to get rid of this I here. So now we have our equation. I just need to subtract 4 on both sides, and y is going to equal 7. So my answers here would be x equaling 4 and y equaling 7. Next, find the values of x and y that make this statement true. So I'll combine our real parts. We have 5x plus 13 equals a -2. And the imaginary parts, I have 2y minus 7 equals, that would be a 1. And that would be a 1 because we're just looking at the coefficient. So this is just 1i. Okay, so now let's solve. So we're going to subtract 13. We get 5x equaling a -15. Divide by 5. X would equal -3. Here we're going to add 8. And we get 2y equaling, or not add 8, add 7. Now we'll make this 8. Divide by 2. Y would equal 4. So x is -3, y is 4. Next, find the values of x and y for this one. So we have 2x plus 8 equaling 2. And then our imaginary parts, we have y plus 11 equals a -4. So subtract 8, get 2x equaling a -6. Divide by 2, x would equal a -3. Here, subtract 11, and we have y equaling -15. So our two solutions would be x equaling -3 and x and y would equal a -15. 5, we're going to add and subtract complex numbers. So again, when we add and subtract, we're just adding real with the real and imaginary with the imaginary. So for this first one here, we have 8 plus 3i minus 4 minus 10i. So we want to combine our real with our real and our imaginary with our imaginary. So our reals would be 8 minus 4, or we could do 8 minus 4. Then we're going to be adding, here we have 3i minus a negative 10i, which just means plus 10i. Now we have, this will give us 4 plus 3i plus 10i is 13i. So my answer here would be 4 plus 13i. Next, simplify this one. The real parts, I have negative 5 minus a negative 3. And then we're going to add 5i minus 8i. So this will give us negative 2 plus a negative 3i. Or you could just do negative 2 minus 3i. Either way, that would work. Next, simplify this one. So the real, that would be 3 plus 1 plus negative 7i plus 11i. We combine that, we get an answer of 4 plus 4i. And another one from example 6, we're going to now use a word problem. It says the voltage V of an AC circuit can be found using the formula V equals CI, where C is the current and I is the impedance. If C is 3 plus 2J amps and I is 7 minus 5J ohms, determine the voltage. We're just going to substitute our values in. So C is 3 plus 2J and I is 7 minus 5J. And then we're just going to FOIL it. So 3 times 7 is 21. 3 times negative 5J is negative 15J. 2J times 7 is a positive 14J. And 2 times negative 5J is a negative 10J squared. Now treat the J just like I as imaginary unit. When I combine these, I have 21 minus J minus 10J squared is negative 1. That's just like I squared, which is negative 1. So now we have 21 minus J plus 10, which will give us an answer of 31 minus J. And that would be our answers. These would be volts. Next, use the formula V equals CI to determine the voltage V of a circuit with the current C of 2 plus 5J and the impedance I of 3 minus 4J. So V equals 2 plus 5J times 3 minus 4J. Going to FOIL it, so that gives us 6 minus 8J plus 15J minus 20J squared. Combine, so I have 6 minus, or plus 7J minus 20 times negative 1. So this is 20 plus 6. We have 26 plus 7J, and that would be our volts. Example 7, divide complex numbers. So here we're going to rationalize the denominator to simplify. So I'm going to multiply this by 3. Instead of plus 2i, it'd be minus 2i in the top and the bottom. Then just treat this bottom one as a difference of 2 squares. Okay, so if I take the first term, 3 and square it. That gives me 9 minus 2i times 2i will give us that would give us a minus 4i squared. And I squared is -1, so this would really be 4 plus, or 9 plus 4, which would give us 13. If this gives us 13 down here, on top I just distribute. This will give us 15i minus 10i squared, which will give us a -1 times -10, which is a +10. So I would have 10 plus 15i all over 13. Now, this should be in proper form of a plus bi format. So if I put that in that format, my answer would equal 10/13, that's my real part, plus 15i over 13. This would be the appropriate form to write our complex number. Next, multiply this by the conjugate. So this would be -4 minus 3i all over -4 minus 3i. So if I do the bottom and FOIL that, or do the difference of two squares, that gives us 16 minus 9i squared, or -1, which will give us 25 in the denominator. Here, that gives us -8i minus 6i squared. This will make that -6 times -1, which will give us a +6 minus 8i all over 25. Put it in proper form, 6 over 25 minus 8i over 25. And our last question here. Divide complex numbers here. So we're going to multiply by the conjugates. 6i, or just multiply by itself. So 6i times 6i. So we can get rid of the imaginary part here. So 6i times 6i is 36. I squared, which would be a -1. And on top, you would have 42i minus 18i squared. If I simplify that, this will give us negative, or a +18. So 18 plus 42i all over a -36. Simplify that, and we would have 18 all over -36 plus 42i over 36, and I can simplify that further. This would give us -1/2 minus, I can divide this by 6, and that would give us 7i all over 6. And so this would be our solution. That's our lesson on complex numbers.